Okay, so good afternoon. My name is Rachit Verma. I am a PhD student at IIT Dharwad. So I am serving as the NPTEL TA for this course, Foundation of Cloud IoT Edge ML. The professor for this course is Dr. Rajiv Mishra, and in this week, we have discussed three topics. Firstly is Edge AWS. Just a second. So firstly, we have discussed how to use ML Edge on the AWS platform. We have discussed federated learning, and we have also discussed autonomous driving, edge computing edge and cloud computing in the context of autonomous driving, and some of the machine learning models that kind of go with that. And so one second, I just admit some participant. Okay, fine. So, so in this session, we're first going to be going over a short summary of whatever had been taught in the last has been taught in this last week. Then I have a few questions prepared from lecture 20 and lecture 21. So for lecture 22, I will be sharing the MCQs with you through the Google form, sorry, through the public sheet, and you can go through that over there. Okay, fine. So hope the screen is visible. So we first started off with introduction to Edge ML with AWS IoT, and we saw you were introduced to AWS IoT, and you saw the basic architecture, the services suite. You saw each component of the AWS IoT architecture, which include things, cloud, and intelligence. You saw some of the building blocks. Of AWS IoT, IoT core, and then you saw what greengrass was and how it corresponds to edge computing, and you saw some of its how the AWS greengrass brings the capabilities of the cloud to the edge. You saw AWS IoT greengrass's various components, and then after that you saw AWS IoT, the event-driven architecture with sensor data, which means you saw like a real life example of how a lot of these AWS services, they come together to how they come together to form the complete IoT cloud edge architecture. And then we saw the various phases of an event-driven architecture with sensor data. Basically, this diagram was also explained, and we saw a use case in the context of greengrass. We saw how greengrass could be used for machine learning inference, and we saw some technical details also over here. And then we saw how greengrass could be used for ML inference. We saw how deployment could be done, and then after that testing could be done. And then we went on to discuss federated learning at the edge. So we will see why there's a need to shift. Over here we saw why there's a need to shift from centralized machine learning training to decentralized machine learning training. We discussed the current IoT scenario from as estimated by various companies and probably think tanks, and we saw how much traffic there is. And then we discussed the shift from centralized to decentralized data, and we saw how federated learning is relevant, how it is a form of we saw how you could say it is kind of like a form of distributed machine learning, although both are not exactly the same. We saw some of the environments that you could use federated learning in, such as PySwift, TensorFlow, Federated Fate, Flower, and Substra. And we saw how multidisciplinary federated learning is. And then we saw the process of federated learning. We saw an algorithm. So by the gradient descent, if you are unaware, it is it happens on like a single model. Uh, we saw how the we saw the various steps of gradient descent and how you could use it to update the weights of a model, and then after that we saw federated learning, like in the context of edge computing, how it could be used. We saw the loss function over here, sorry, or you could say we saw the error function over here, if you are unaware. So our objective is actually to minimize this error function. We saw what the negative over here basically, like maximization and minimization is equivalent if you add this negative log over here. And then we saw just a second. And then we saw federated averaging. We saw federated learning in the context of identical and yeah, independent and identically distributed data. And then we saw a simple image classifier using federated averaging. We saw how Apple works, how Apple uses federated learning for training, and we saw the entire training process of federated learning. We saw the challenges of federated learning, and then we saw how it was different from distributed learning, and then we saw some of the concerns that are associated with federated learning. Then we went on to discuss machine learning for autonomous driving. Okay, we saw so in this one we were introduced to autonomous vehicles over here, and it was the US state. There's an alarming, interesting fact that the US State Department of Transportation said that self-driving cars could reduce the 90% of traffic deaths. Okay, then we saw how edge computing could be used for in the context of automotives, and we saw how this how this automotive application is actually mission critical. It's actually latency critical. So it said that when driving a vehicle milliseconds matter. Okay, so we then saw self-driving car sensors, and how edge computing could be used in that context. We saw the requirements of self-driving cars. So this includes pre-processing collected data, securing network connectivity, and high performance computing. We saw how machine learning trains how machine learning trains AI in self-driving cars. So we saw that it could be modeled as a regression problem. We then saw what Kalman filters were. Okay. We then saw some more components such as the lidar, radar, and the camera. We saw the relevance of vehicle to vehicle communication, and then we saw the key components of machine learning for self-driving cars. This includes perception, sensors, scene priors, and then we saw like some practical examples over here. Okay, like so this is like object detection and labeling. We saw that as well, and we saw like semantic object segmentation. So how all this is very important for self-driving cars. And then after that we saw how to do time tracking using embeddings or recurrent neural networks. So I mean time tracking in the context of how different objects will be tracked over time. Okay, we saw like very surface of this. We saw what the Waymo open data set is. Okay, we saw what kind of data you need for training models in self-driving cars. So these include the labels, the coordinate systems, acceleration. We saw how LSTMs could be used for self-driving cars. We saw the performance of some of the state-of-the-art methods in the self-driving cars, and then we saw the trends, some future trends for autonomous driving as well. Okay, fine. Okay, so let's begin with the questions. So now we're going to be starting with lecture 20. Okay, so you all can, yeah. So is previous session uploaded somewhere? Yes, previous session has been uploaded in the if you go to the public sheet, right, the public sheet will have links to all the 7 sessions that have happened till now. So this is the 8th session, which is the final session. Okay, and after this I think you'll be asked to appear for the exam. So best wishes everyone. Okay, so question 1 is, what is AWS IoT? Is it A, a software development platform? Is it B, a cloud based service for IoT devices? Yeah. Is it C, an operating system for IoT devices? Or is it D, a hardware manufacturer for IoT devices? Okay, B. This is very simple. So it's obviously not a software development platform. So AWS IoT may have an SDK, but of course we don't use it to develop software. It is used for the facilitating this interaction between cloud and IoT, right? So that's why it is B. It is a cloud-based service for IoT devices. Okay. Let's go down further. So what is AWS Greengrass? Is it A, a cloud computing service? Is it B, an edge offering for IoT platforms? Is it C, a machine learning algorithm? Or D, a communication protocol for IoT devices? It's a cloud computing service. So yes, so AWS does offer it, but are you sure it is a cloud computing service? That wouldn't see all of this. Everything that AWS offers is a cloud computing service, definitely. But fundamentally, it is what is it? Uh, like what is it actually facilitating? Uh, okay, fine. So there are no responses. So B. So the answer to question 2 is B. It is an edge offering for IoT platforms. So if you are a little confused about this, let's go to your notes and see what is being said. So yes, so now it does say that Greengrass extends AWS IoT to your devices. So they can act locally, and the data that they generate or filter is filtered before it is sent to the cloud. Okay, but what devices are actually doing that? Right. So let's take a look. So fundamentally, the AWS Greengrass group, it is trying to bring cloud capabilities to the edge. Okay, so like how is it doing this? Um, okay, I'm unable to find that right now. So there is a section about this in the slides as well. Let me see if okay, fine. So it is not directly apparent. Uh, okay, fine, fine. So you can take a look at this image over here, right? So it says over here, AWS Greengrass. So extends AWS IoT to the edge. So AWS Greengrass extends AWS IoT onto your devices so that they can act locally on the data that they generate while still taking advantage of the cloud, right? So so you can say that over here as well. So AWS, these devices that are being talked about, AWS Greengrass extends AWS IoT to your devices. So these devices that are being talked about are edge devices. Okay. So I hope from this it is clear that AWS Greengrass, it is an edge offering for IoT platforms. Okay, so it is not a machine learning algorithm exactly. So you can run machine learning algorithms on the edge with the help of AWS Greengrass and a communication protocol. So that's not true either. We have like MQTT and all those things. Sorry. So the third one. Um, so wait just a second. Okay, let's finish this quickly. So, what is the main issue with IoT data processing in the cloud? So, this also comes from your first lecture, but we need this context. I think you can answer this question very easily. Bharat says B, high latency. Okay, why is that? Are there any other responses? Okay, before I continue, I just want to say that these questions were prepared by Rajneesh Verma and Shweta Verma with the help of some some AI tools and such as ChatGPT. Okay, someone has said D. Okay, so D could be, yes. So sometimes security concerns could be there, definitely. If you're actually transferring data from the IoT to the cloud, you could have many people trying to eavesdrop, or many people who are trying to, let's say, spoof or intercept or do intercepts or something like that, right? So so definitely security concerns could be there, but of course, like security concerns aren't as prevalent as something like high latency, right? So almost, sorry. So you could have a very large number of people. Uh, you could have very large number of cases where you're experiencing latency issues, but you may not have as many like security concerns. So if it was multi-correct, we could say you could actually say B, C, and D. Okay, but if it is single correct, yeah, actually it could still be B and C. Okay, so let's take B, C, and D as the answers to this question. Okay, for 3 it is B, C, and D, not just B. Okay, so let's do sixth one. So what does the AWS? Oh, sorry. So what does the AWS IoT architecture consist of? Is it A, two layers, a cloud and edge? B, huh? B, yeah, okay. B, three layers, things, cloud and intelligence. C, four layers, sensors, connectivity, cloud and analytics. Or D, five layers, devices, connectivity, cloud, analytics and visualization. Any other responses? Okay, yes. So the answer is definitely B. If we go into your slides as well, and we try to look for the various components, you have over here things, cloud, and intelligence. The things can contain sense and act. Cloud can contain storage, compute, learn. Intelligence can contain business logic and analytics. But what is over here, right? Things, cloud, and intelligence. Sorry. But fundamentally, these things, cloud and intelligence, all these other things, connectivity, cloud and analytics, all of this will come and all of these will come under this things, cloud and intelligence. Okay, whatever is there. So these are like subparts of it. Okay. So let's do this also quickly. So what does AWS Greengrass offer in the context of IoT? We've just, yes, edge computing capability. Okay, so it extends IoT devices, whatever capabilities of IoT devices to some nearby devices. Thus, you can say it's like an edge device. Okay. So what is the primary function of AWS IoT core? Is it A, device registration and management, B, edge computing at the device level, is it C, cloud based machine learning, or D, sensor data synchronization? So is it A, device registration and management, B, edge computing at the device level, C, cloud based machine learning, or D, sensor data synchronization? AWS IoT core, device registration and management, edge computing at the device level, cloud based machine learning, or sensor data synchronization? Okay, we said B. Fine. Any other responses? Device registration management, edge computing at the device level, cloud based machine learning, or sensor data synchronization? Okay, fine. So let's take a look at your notes, right? So the answer is A, device registration and management. So if we take a look at your notes, right? So what does AWS IoT core do? It's about connecting devices to the cloud the moment you bring in your first device that is going to become available. Okay. Um, so so fundamentally, like it's you connect your devices over here, and the moment you register a device, you receive a set of credentials for the device, and you're going to embed those credentials in the device. And once the device has those credentials, it connects to the cloud, gets authenticated, authorized, and it shows up in the device registry. Okay. So what is it doing? So fundamentally, it is doing device registration and management. So where's the registration part? This authentication, authorization, and showing up in the device registry. Like this is the registration part. Okay. And where is the as far as the management is concerned, I mean fundamentally you could say, right, it is like all this kind of falls under management as well. Okay, so management could be said in the context of, let's say you have some messages that you want to pass, right? So you may use something like MQTT or like WebSockets or HTTP or something like that. So you could say like management also like comes over here in the AWS IoT core. So which protocols are supported by AWS IoT for machine to machine communication? Is it A, FTP and SSH, MQTT, WebSockets and HTTP? Is it C, SMTP and POP3? Or is it D, SNMP and Telnet? Okay, Bharat says B. Are there any other responses? B. Just one second. Okay, fine. So, uh, fine. So you have all said. So quite a few are saying it's B. So let's go in and check that out. Okay. So message broker, which is based on MQTT, WebSocket, and HTTP for publishing subscribing messages for feeding data from the device to the cloud. So you can say so because of that you can say MQTT, WebSocket, and HTTP is used. So this is kind of like machine to machine communication. Okay, and it is predominantly uses it for a communication between devices at the cloud to send some metadata or telemetry. Okay, but it is predominantly used for a communication between devices at the cloud. Okay, so you can say from that context that from like this is like the equivalent of machine to machine communication. Okay, so that's why we're using MQTT, WebSockets, and HTTP. So because of that, the answer is definitely B. So what is the purpose of AWS IoT device management? Is it A, to synchronize sensor data with the cloud? Is it B, to provide edge computing capabilities? C, to manage and onboard IoT devices in bulk? Or D, to perform analytics on IoT data? Synchronize sensor data with the cloud. So sing some C. Okay. Okay. Any other responses? Fine. So there's A and C, right? A, C, and D. Okay. So does IoT device management perform analytics? So no. So okay, fine, fine. So let's see your notes once again. Okay. So so just take a look at this paragraph over here. So IoT device management supports bulk onboarding of devices because registering one device at a time in industrial use cases is not feasible. So from this we can say that IoT device management is responsible for bulk onboarding. So now some of you were a little bit confused with the idea of synchronization. So like when we are like working with device shadows, then like the idea of synchronization kind of comes in. So let's see if I can like find that in your notes. So over here the device shadow is the digital twin or the digital identity of the physical device. All changes that are made to the device will first get applied to the device shadow, then get propagated all the way to the device. Okay, so So like in that case, like some amount of synchronization could be happening, right? But it kind of like comes under this AWS IoT core. Well, okay, you could kind of say that like these two are kind of related, but it's not exactly like like IoT device management. Like it's not exactly that which is uh, like at least from your notes, it is not exactly that which is doing the device shadowing. Okay. And okay, analytics is obviously not performed by device management. That for that there is another service that is actually doing the analytics. Okay. I think we have AWS IoT like analytics over here. That is a part of like the intelligence layer. So device management is not doing the analytics, at least from your notes. Okay. Let's go to the next question. So which operating system is recommended for IoT devices in the AWS ecosystem? Is it Windows, Linux, Mac OS, or Amazon Free RTOS? So which operating system? D. Okay. Yes. So D. Okay. Okay. Good. Very good. So which operating system is recommended for IoT devices in the AWS ecosystem? Windows, Linux, Mac OS, Amazon Free RTOS. Okay, so does anyone want to like tell me like why exactly we won't use something like Windows, Linux, or Mac OS on IoT devices? So we have explained this quite a few times, maybe not in the lecture, but somewhere directly or indirectly. If someone wants to unmute their mic and tell me why exactly why exactly we don't use Windows, Linux, or Mac OS.
Memory.
Yeah, memory is definitely a constraint. So yeah, so memory is one thing. So these memory in the sense it could be RAM as well, RAM. So these IoT devices may not have enough RAM to actually. Yes. Anyone wants to say something? So definitely RAM is a constraint, or it could even be that these don't have enough like HDD space as well. That is why we have these kind of lightweight OSs for IoT devices. You want to say something, Anil? Uh, okay, I'll be muting you.
I meant ROM actually, where OS is loaded actually. The
Hmm.
OS is loaded in ROM, right? The
Hmm.
space. So I meant not only the RAM which is used for
Yeah.
current
Okay. Okay.
processing. I meant ROM where
Yeah.
the
The
Mac
bootloader
and all.
is. Yeah.
Mac takes up a huge space
Hmm.
uh, in the ROM memory. I don't.
Okay.
That's what I.
So I'm not aware of the exact details, but I think from what I remember, like the bootloader of an OS is kind of loaded in the ROM, right? It's not the like. I could be wrong. Like I have to revise my OS notes. Anyway, let's just take a look at your notes. So, uh,
Okay,
so
so googling it, I just saw first it is stored in ROM and then a copy of it is stored in RAM during boot up.
okay, okay. Fine, well, let me check it out.
Yeah, both spaces. Uh,
Okay.
On means when it is switched off, it has to be in ROM, and then move to RAM at boot up.
Okay, okay. Mm-hmm.
So the bootloader sequence will take it from ROM to RAM for faster
Okay,
process.
okay. Okay, thank you. Thanks for that. Um, so when will week 5 to be? I will do it today. Okay, I will. I'll do it by Sunday evening if that's fine. Okay, when will week 5 to week 8 tutorial materials be shared? So, like by Sunday if it is. Like I just have to make some changes to these lecture notes, then I will like send it to you. Oh, I'm sorry. Okay, anyway, let's just read that. Amazon Free RTOS is a real-time operating system which can run on top of a microcontroller with 64 kilobytes of memory or more. Okay, so basically, free RTOS it's very lightweight and it can run on like very less memory as well. Okay, so let's go to the next question. So, what role does AWS Greengrass play in the AWS IoT architecture? So, is it A? It acts as a cloud storage service. B. It provides local triggers and actions at the edge. C. It performs analytics on IoT data. Or D. It manages device connectivity. Okay, can I just want to ask you one more question. When is the exam for this course? When is the exam for this NPTEL course? I am actually unaware of 21st April.
Next Sunday.
Oh, okay, then I'm fine. Then I'll share this week 5 to week 8 as soon as possible. I'm sorry for the delay, um, but I hope the videos were like somewhat helpful. Okay, fine. What role does AWS Greengrass play in the AWS IoT architecture? Um, so, some of you have. Please mail me any PDF material to this. Do you have access to the public sheet? Like it's there on the course page. If you don't have access, then I'll just show you how to. I hope you're not wasting too much time on this. Anyway, I'll just email you the public sheet, okay, on this av.panindra at gmail.com. Just make a note of your email address somewhere here. Or do one thing, just send me an email on this. Okay, I will respond with I will respond with the public sheet. Send me an email to this on this ID. Okay, I will respond with all the whatever relevant PDFs and all that. Okay. So what role does AWS Greengrass play? Um, yeah, just Sharwani, you can just send me. Uh, okay, yeah. Someone has said B and D. Okay, fine. We can. Okay. Yeah. You're just waiting for me to upload it, right? I will do that. Soon. Okay. Fine. So some of you have said B and D. So let's take a look at that. So B is obviously correct. Okay. I'll just point to your notes. Yes, over here. Um, So okay, I'll just read this paragraph out. So like AWS IoT code, there's a message broker built into Greengrass, so devices can continue to talk to each other. So there is a compute layer which is based on Lambda to write functions that are running locally and triggered when a specific condition is met, and these triggers will actually fire Lambda functions that perform an action. Okay, so what is happening is uh, so these Lambda functions, right? I don't know if you remember like function as a service. Okay, when we were in function as a service in the very first lecture. So what AWS Lambda does is it provides something called function as a service. Okay, so like a function is like a very like short and like lightweight kind of piece of code that you can run. A function is like very light, like short, lightweight piece of code that can be triggered upon when you kind of place a request or something like that. Okay, or basically let's say there's an event that happens, you can set up a function to be triggered, and when the function is triggered, it will run some kind of code. So that is kind of also happening over here. Okay, so so there's a message. So like as usual, there's a message broker built into Greengrass, and there's also a compute layer which is based on Lambda. So when like some kind of function specific conditions are met, these triggers will fire Lambda function that perform an action. So I'll give you like one small example. So uh, let's say AWS Greengrass, it kind of receives some sensor data for that is in Fahrenheit. So you can write a Lambda function so that is triggered only when let's say you receive data of a certain format. Okay, so let's say now what this now like this condition, right? So it will check um, so or not only that, you have to write a you can write a condition, you can write a function that is triggered like the moment you receive some kind of data. Okay, so so let's say the moment you receive sensor data, like you can set up this Lambda function in such a way that is triggered when this Lambda function is uh, that is set up such that it is triggered when you oh my god, I'm just repeating myself 3 times. So basically, in short, let's say you have an event. That event, something will check for that event whether it happens or not. If it says that event has happened, it will trigger a short piece of code. So now this piece of code will be present inside something called a Lambda function, and this Lambda function, it can do something with whatever event has happened or with whatever data that has been given. Yeah, fine. Let's go to the next question. So what is the role of AWS Device Defender in the AWS IoT architecture? Is it A, analyzing sensor data trends? Is it B, managing device data, managing device authentication? Is it C, providing security and alerts for device fleets? Or D, handling telemetry synchronization? Okay. C. Shivani also says C. Okay, right. So yes, so you're correct. So AWS Device Defender, it provides security and alerts for device fleets. Okay, so let's take a look here. Mm, so it automatically raises alerts if there's a drift between the preferred configuration and the policy. Okay, and also maintains a secure footprint of all the devices. Okay, so in this context, you can say that AWS Device Defender, it provides security and alerts for device reads. Alerts when, so if let's say there's a drift between the preferred and like the current configuration, okay, and the policy what is currently running, and security why, because secure footprint of all devices, and if there's any anomaly. Okay. So now over here someone had like discussed this IoT analytics, but okay. So what function does AWS IoT analytics serve? Is it acha, B? Is it A, managing device firmware updates? B, analyzing trends and visualizing data? Is it C, providing machine learning algorithms? Is it D, handling device registry and authentication? Bharat has said B. Are there any other responses? V. Okay. Okay, fine. So okay, fine. So let's look at your notes. So it is responsible for AWS IoT Analytics is an analytics solution, and this service is responsible for analyzing the trends, visualizing, analyzing. Sorry, and analytics solution, and this service is responsible for analyzing the trends, visualizing, and from there feeding to more powerful systems like QuickSight or Redshift and so on. Right. So because of this, you can say that IoT Analytics, AWS IoT Analytics is responsible for analyzing trends and like visualizing data. Okay. Obviously, data is implicit over here, but you can understand that. So, what is the primary purpose of AWS IoT Core? Is it A, analyzing sensor data? Is it B, managing device hardware? C, connecting devices to the cloud securely, or D? C. Okay, connecting devices to the cloud securely. Hi, sir. Are there marks for weekly assignments? Yes, there are marks for weekly assignments. So let's take a look at your notes. Right. So AWS IoT Core is all about connecting devices to the cloud. The moment you bring in your first device that is going to become available, you need to talk to AWS IoT Core. So you can say that yes, devices are being connected to the cloud. Okay, and then now how do you know that that this device is being connected to the cloud securely? So you check over here. The moment you register a device, you receive a set of credentials for the device, and you're going to embed those credentials in the device. And once the device has those credentials, it connects to the cloud, gets authenticated, authorized, and shows up in the device registry. So all of these things correspond to the security. Okay, so this credentials, this authorization, authentication. That is why this we want to make sure our device is being registered securely. Okay. So which service is responsible for maintaining the digital twin of a physical device? Okay, let's take a look at this one. So is it A, AWS IoT Core, B, AWS IoT Device Management, C, AWS IoT Analytics, or D, Device Shadow of AWS IoT? Which service is responsible for maintaining the digital twin of a physical device. Device shadow. AWS IoT Core, AWS IoT Device Management, AWS IoT Analytics, Device Shadow, AWS IoT. Hmm. D, okay. Any other? Okay, everyone is saying D, so I don't think there's any confusion. So why not B? Okay, fine. So this is also very simple, but still, like the intention is that you understand your nodes. Okay. So in AWS IoT Core, the device shadow is the digital twin of the or digital identity of the physical device, and all the changes that are made to the device will first get applied to the device shadow and gets propagated all the way to the device. So we had just discussed this in the context of synchronizing the device to the cloud and all those things. So when the device state changes, it automatically gets synchronized with the device shadow and acts as a buffer between the desired state and the current state. So you can say from here that whatever is being asked over here, that maintaining a digital twin of a physical device, that is being done by device shadow. So over here is digital twin of a physical device. So what role does the rules engine play in the AWS IoT Core? Is it A, managing device connectivity, B, maintaining device firmware, C, filtering and applying rules to messages, or D, synchronizing device data with the cloud? C, filtering and applying rules to messages. Okay. Any other responses? Okay, I'll give you all 1 more minute to respond and then we'll see. C. Okay, everyone is saying C. Does okay, fine. So this also looks very simple. Yes, so C is the right answer. Filtering and applying rules to messages. So very specifically, what does it do? Let's see your slides. Right. So there's a rules engine over here. It decides how the messages will flow into the rest of the system. So it is a building block of the AWS IoT Core, right? And over here the rules engine is ANSI SQL compliant, and it writes simple select statement that will filter the messages and apply a rule, and the outcome of this rule can be hooked to a lambda function to take further action. So lambda functions, I hope you all are clear. Does anyone want me to explain what lambda functions are? Okay, fine. So lambda functions. Okay, so let me see if I can show you all AWS lambda architecture. I think this lambda function, it requires a good amount of explanation, because anytime you try to do something in the cloud, right, you will need some kind of lambda. Mm. Mm. Okay, fine. So let's do some very simple. Let me take a very simple example over here. Okay. So let's take a very simple example. So let's say you want to upload a photo. Okay. You and upload a photo to a website. So how will you upload it? So you are you aware of what S3 is? So you know how Google Drive works, right? So in Google Drive you kind of like upload things. So in just the same way, like we have a service called Amazon S3. So Amazon S3 also allows you to upload some kind of files or images to it. Okay, and and so now just keep this in memory for now. Okay. So let's say I'm trying to build a very simple, image uploading kind of service. So in an image uploading service, we have like a client, and we have a server. Okay, so now the client will upload the image, and the server will, let's say, read the image, and let's say it will, display it on some kind of website. Okay, but now this client and server, right? Both of these have, let's say, some problems with like communication in the sense that the server the client will upload an image of let's say 512 by 512, but the server wants an image of, let's say, 1024 by 1024. Okay, so now what you can generally do is you can like upload this image to the server, sorry, to some kind of storage service, and the server will take the image from the storage service and will display that faulty image. Okay, because let's say the server is expecting 1024 by 1024, but it is not getting 1024 by 1024. Okay, so now it will display a faulty image. But what you can in order to rectify this, what you can do is, one simple thing is you can you can create something called a lambda function. Okay, or you can set up something called the AWS lambda service. So what the AWS lambda service will do is, okay, it will hold some code inside it. Now this code will will be responsible for reshaping an image from to, let's say, 512 by 512 to 1024 by 1024. Okay, so um, uh, so it will hold some code there, like it'll just keep it there. But now when will it be run? You can program that lambda function in such a way that it is run every time something is uploaded to Amazon S3, or every time something is uploaded to the storage service. So fundamentally what is this lambda function doing is, it is what is happening here is, we have something that is running this lambda function only when something is uploaded. And what is it running? It is running some code to resize the image. Okay, so very simply put, like this lambda function, right, it contains some code inside it. Okay, that you can set up in such a way that it is run only when some kind of event happens. Okay, so that same logic will come into Greengrass also. So I hope it is clear. Like there's some short snippets of code inside this AWS lambda, and you can set it up to run in such a way only when an event happens. That is the fundamental idea behind what is like function as a service. Okay, how did we come to lambda functions? Anyway, so now the same thing happens over here as well. Okay, so this short snippet of code, right? Okay, so this short snippet of code, okay, like this will be executed once this rule engine has already done whatever filtering and whatever selection it has to do. Okay, so this short snippet of code will be inside the lambda function. It will be run based on the whatever output comes from this rules engine. Okay, you can skip this. Okay, fine, we'll just quickly do it. Which service handles the registration and authentication of devices in AWS IoT core? Is it A, AWS IoT Analytics? I know I've showed the answer, but still, like, you can just check. Okay. So, okay, device management and device registry. Okay, fine. There's some confusion between these two. Okay, which service handles the registration and authentication of devices in the AWS IoT core? So, what is the device management, right? Let's take a look. So, IoT device management, it does bulk onboarding of devices. Okay, but the device registry, the device registry over here is it responsible, it's responsible for registering devices. So now there's a difference between like onboarding and registering, right? So registering will like have all this authentication and all this as well. uh, so like so okay, so I hope this like okay, wait, so okay, how do I explain this? um, so the AWS IoT core, okay, so you can say that it is acting like a device registry, but the IoT device management over here, it is responsible for bulk onboarding. Okay, so bulk onboarding, so like if you want to like onboard like multiple devices at a time, you will do this device management. But but the device registry over here, it is uh, like it actually has like all the registration like of all the uh, of all the devices. Okay, so you can say like um, okay, fine. Let's actually skip this question. I can see that there is some amount of ambiguity in this one. Okay, it'll be a little bit hard to explain this. Fine. So, what role does the AWS Greengrass core serve in edge computing? Is it A, providing local storage for device data? Is it B, enforcing consistent? Yeah, you could say that. Like, um, but it is showing up in the device registry, but the device registry exactly is not doing the authentication process, right? It could be a device management that is doing the bulk onboarding over here. So the registry, like it kind of you can say it contains all of this, all the registrations. Okay, so it may not be actually doing it. Okay, no, I understand. No, I'm not talking about you. Sorry, I'm not talking about you, Bharat. Actually, Panindra had given us a response over here. The moment you register a device, you receive a set of credentials for the device, and you're going to embed those credentials in the device. And okay, so over here, yes. So there could be a slight mistake over here. The device registry is not exactly handling the authentication exactly. The registry, like it kind of contains the it kind of like contains all of the like the parameters pertaining to each device, but the actual registration and authentication would be handled by the device management over here. Okay, so okay, so this kind of may be mistake a mistake on my part. So over here, yeah. So what role does the AWS Greengrass core serve in edge computing? So you have said D. Bharat has said D. Um, so yes. Okay, fine. We'll look at your notes as well. So providing local storage for device data, B, enforcing consistent configuration and policy for devices, handling data ingestion, acting as an edge device that runs local computing tasks. Any other responses? So Bharat says D. Okay, fine. Let's take a look at your notes. So, so the AWS IoT Greengrass core is just a device in AWS IoT core registry that doubles up as an edge device. It is an x86 and ARM computing device running the Greengrass runtime. Local devices talk to the core similar to the way they interact with the AWS IoT core. So basically, it's an edge device. It doubles up as an edge device to be more precise. It has x86 and ARM computing. It is an x86 and ARM computing device, okay, and it has the Greengrass runtime as well. So because of that, you can say that for 20, D is the correct answer. So local devices, well, it may not exactly run local computing tasks, but local devices can definitely talk to the core. Okay. So how does AWS Greengrass facilitate machine learning inferencing at the edge? Oh, I'm sorry, just 1 minute. I don't know why. Is it A by providing? Sorry, is it A by providing direct access to the cloud-based machine learning models? Is it B by synchronizing data with the cloud for inferencing? C by running machine learning models locally on edge devices? Or D by offloading inferencing tasks entirely to the cloud? C. Okay, any other questions? Any other responses? So offloading is not happening on Greengrass, right? Well, maybe you may have some task that is offloaded from IoT to the edge, but this offloading is not. But we don't know exactly if offloading is happening uh, from edge to the cloud because of Greengrass. At least it's not yet in your notes. Okay, fine. So let's take a look at your notes. So the question was, um so basically, the most recent feature of green grass is the ability to run machine learning inferencing on the edge, and this is one of the key drivers because there are three aspects when it comes to IoT. So there's obviously learning part, and there's the decision making part, and and obviously there's the training, and of course, basically there's a learning part, then there's a decision making part. Okay, in this. So, but fundamentally, we can see here that the most recent feature of we can see that like green grass has the ability to run machine learning inferencing on the edge. Okay, and it is one of the one of the key drivers because there and it is one of its key drivers. Okay. So synchronizing data with the cloud, so that's not handled by green grass. You can say that device shadowing does that. Direct access to cloud based machine learning model, that's also not true. You would have to send like data to the cloud for that. Offloading, we are not exactly sure if it happens on green grass. So what is the purpose of the AWS Greengrass group? Is it A, managing device authentication? Is it B, defining the scope of interaction for edge devices? C, performing data ingestion into AWS IoT core? Or D, synchronizing device shadows with the cloud? B. Yes, so B. Okay, any other responses? Okay, fine. So, so definitely defining the scope of interaction for edge devices. So that is relevant. So let's take a look at your notes as well. So what does it do over here? So it is a collection of settings and components such as AWS IoT Greengrass core and device and subscriptions. So groups are used to define a scope of interaction. So a group might represent one floor of a building, one truck, entire mining site. So for example, it's like all of these, like you can see as one group over here. Okay, so a group is also, you can say, is the logical boundary of all devices. So intuitively it can also kind of imply that if all the devices that are in one group will have like the same collection, will have the same, let's say, settings or something like that, will have like similar settings at least. So which service enables developers to yeah, scope of interaction, that's correct. Which service enables developers to build complex workflows without managing protocols? Is it A, AWS IoT core, B, AWS Greengrass Lambda function, C, AWS Greengrass connectors, or D, AWS IoT analytics? B, AWS Greengrass Lambda function? Okay, I'm sorry, but is the Lambda function enabling a complex workflow alone? So the Lambda function alone, is it doing that? IoT core. IoT core is responsible for managing devices. Connectors. Okay. Any other responses? AWS green grass connectors. Fine. Yes, so you are correct. So someone had said something about lambda functions. Lambda provides the local compute capabilities. Okay. So lambda functions, you can say, like they have some features. Okay. Okay. Like AWS, but like they alone, they're not exactly allowing you to build these complex workflows. Like the lambda function may be part of the workflow exactly. Okay. But like developing this complex workflow comes from a connector. So let's take a look. So what it says here is AWS IoT Greengrass connectors allows developers to build complex workflows on AWS IoT Greengrass without having to worry about understanding device protocols, managing credentials, interacting with external APIs. Okay, so connects extend the edge computing scenario to third-party environments and services. Okay, so basically, uh, like AWS IoT Greengrass connector, it's what allowing Greengrass to build complex workflows. Okay. So let's do this quickly. So what role does Amazon SageMaker play in the machine learning inferencing process? Okay. Um, is it A, it trains the machine learning model? Is it B, it deploys the trained model to AWS Greengrass? Is it C, it performs inferencing at the edge? D, it ingests data streams for real-time analytics. Okay, says B, it deploys the trained model to AWS Greengrass. Performs inferencing. I mean, SageMaker is performing the inferencing. Are you sure? So is it A? Okay, fine. So let's take a look at your notes. So SageMaker may not be directly performing the inferencing step. Okay. Hmm. Fine. So let's take a look at this. So if you look at the Greengrass machine learning inference, okay. So what happens is, first an Amazon SageMaker training job is to create the model. The Greengrass configuration is being deployed. The Greengrass core will download the model from the Amazon SageMaker training job as a local machine learning resource, right? So this Greengrass core, like it will, like it's running on the edge, right? So in that sense, okay. So that is why you can say that it deploys the trained model to AWS Greengrass. So from there it can do whatever inferencing it wants. Anyway, So let's start this one. So let's start with lecture 21. So why is there a need? So let's start with lecture 21. So this is the federated learning lecture. Okay. So why is there a need to shift from centralized machine learning training to decentralized machine learning training in the IoT domain? Is it A, to reduce the costs associated with cloud computing? Is it B, to overcome the limitations in bandwidth and power for data transfer? Is it C, to comply with regulations and data privacy? Or D, to enhance collaboration between IoT devices? So this can be like multi-correct also, okay? I don't know, it's must be pretty hard to see this. Okay. Anyway, I'll just ignore the answer. You think about it like from the answer could be wrong. Okay, so just think about it from your like reasoning. Why is there a need to shift from centralized machine learning to decentralized? Okay. To reduce the costs associated with cloud computing, to overcome limitations in bandwidth and power for data transfer, C, to comply with regulations on data privacy, or to enhance collaboration between IoT devices. Any other responses? Federated learning, correct. Federated learning is helpful in decentralized machine learning. Okay, fine. So the answer to this question is A and B. No, sorry, not A. Is B and C. So why not A? So A is kind of vague. Okay, we don't really know if. So of course it will reduce storage costs. Okay, because instead of if you do the if you do it in a decentralized manner, so definitely you could say, but still it is kind of vague. So I wouldn't say A is the answer. But okay, fine. Since you're not storing all the data centrally, you could say that A is the answer. And to overcome limitations in bandwidth and power for data transfer. So yes, so when you're sending data to machine learning centrally in a centralized manner, so what is happening is so so when you're sending data in a centralized manner, you are sending data to the cloud so that training can happen in a centralized manner. You're using the network channel, and if you have a lot of data, there could be some kind of cost when it comes to like power or bandwidth. Okay, regulation on data privacy. Yes, this is also very relevant because you may not want to send very confidential data to in a centralized manner to the cloud, so that can be very challenging. So enhanced collaboration, that is not necessarily true. Okay, so this you can just refer to your slides, but you should know this, but you should have like some idea. So what is the projected value of the IoT market in terms of supplier revenues by 2025 according to Gartner? Is it A 11.1 trillion, C 7.1 trillion? Are you sure? So that's not the right answer. projected value of the IoT market in terms of supplier revenue. Just refer to your slides and answer to this one, because you should have some idea of like the potential for IoT, how huge the market is. So what is the projected value of the IoT market in terms of supplier revenues by 2025 according to Gartner? D, 309 billion. That is true. 309 billion is a very huge number. Sorry, what? Let's do this quickly. This could be multi-correct. So, which term is used to describe the machine learning paradigm that uses distributed data? Is it A, centralized learning, B, decentralized learning, C, distributed learning, or D, federated learning? Multi-correct. D and B. So, machine learning paradigm, like decentralized learning is not really the name of the paradigm, right? Or is it? Well, you could say. Fine. So over here you could say the answer is B, C, and D. Okay. But C and D would be more accurate. Like decentralized learning, the term is not as popular as C. Okay. But yes, you could say this like in technical papers and stuff. But C is more popular than B. Distributed learning is more popular than this. The answer would be C and D. So what is the primary goal of federated learning? So is it A, centralizing data for better analysis? Is it B, sharing data across all nodes? Is it C, training machine learning models while keeping data decentralized? Or is it D, moving all data to cloud for processing? Okay, fine. So everybody is saying C, training machine learning models while keeping data decentralized. That is true. Let's take a look at your notes. Well, it may not say this exactly, but it says over here, federated learning aims to collaboratively train an ML model while keeping the data decentralized. Okay, so from this you can say that C is the. Okay, so how is federated learning different from traditional centralized machine learning? It relies on cloud computing for data processing. B, it only sends the model to the central server, not the data. Or C, it involves sharing all data with the central server. Or B, D, it focuses on data localization rather than data privacy. Yeah, that is true. It only sends the model to the central server, not the data. So then this model will then be like you can do federated averaging on like various models to get a single global model. Let's take a look at your notes. Okay. So over here it says a network of nodes and all nodes with their own central server. But instead of sharing data with the central server, we share model. We don't send data from a node to server. Instead, we send our model to the server. By the way, I have written a research paper on this. If you are interested in reading about it, so so if you are interested in reading about federated learning and some sort of analysis on how it can be run, you can read my paper. So the research work for my masters was actually on federated learning. If you're interested in like knowing more about this or how to run experiments, you can like email me. Okay. And here is some of one of our papers that we wrote on this subject. So this can have multi-correct answers. Okay. Yes. So which algorithm is commonly used for training machine? Well, let's not use machine learning models in general. Let's say neural networks. Okay. So which algorithm is commonly used for training neural networks in federated learning? Okay. Is it A, backpropagation, B, support vector machine, C, gradient descent, or D, random forest? So Bharat has said B. So support vector machine is not really a training technique, right? So the entire machine learning technique in that case would be called is called support vector machine. Support vector machines, it kind of uses Lagrangians uh, to learn a hyperplane, if I'm not wrong. So it does not. It's not really a training technique. And also we're planning I'm writing the question specifically for neural networks. Okay, gradient descent. Okay. All right, you're saying okay. Damn, I got scared. Okay. So anyways, so yeah, so gradient descent is an acceptable answer, but even backpropagation, like so how it actually happens is through backpropagation. Okay. So we try to minimize the loss through gradient descent, but the gradients of on each of the neurons in a neural network are updated through backpropagation. So yeah, so gradient descent is the correct answer, but you should also keep in mind what backpropagation is doing. So what is the purpose of gradient descent in machine learning? Is it A, to calculate the cost of coefficients? Is it B, to maximize the probability of the output given input? C, is it to minimize the error function? Or D, to initialize the model parameters? Calculate the cost of coefficient. Which coefficients? First of all, if you had said something like weights, maybe. First of all, the coefficients. First of all, we don't know like which coefficient. Wait, just a second. I think there's a. Hello. I'm really sorry, there was a problem in the internet. I'm really sorry about the connection. There was a problem with the internet. I hope everything is. I hope I'm visible now. I'll just share the screen once again. Just give me a few minutes. Let's let this set up. There's a slight problem with the internet over here. Okay, I hope the screen is visible. Oh, okay. My voice is breaking. Okay, I'll just somehow manage. Okay, so we were at here. So which algorithm is commonly used for which algorithm is commonly used for training neural networks in federated learning? Yes, so the answer is backpropagation and gradient descent both. Gradient descent would be the most appropriate answer. Backpropagation is used to update the weights, in neural networks. And what is the purpose of the gradient descent procedure in machine learning? Is it A, to calculate the cost of coefficients? Is it B, to maximize the probability of output given input? Is it C, to minimize the error function? Or D, to initialize the model parameters? Anyone have any responses? Calculate the cost of coefficients, but we don't know which coefficients exactly they are, right? So, C, yes, so minimize the error function, yes, so that is the correct answer. So the error function basically quantifies how much error is there in our prediction in the ground truth, and we want to minimize that. Yes, you want to say something?
Yeah, so there was something called cost or loss function that Sir described the method. So is this, it was trying to minimize the cost function with the current coefficient. So wanted to know if this error function you mean uh, the cost function or the loss function.
Um, wait, so like the
Or
cost and loss are like interchangeable, but what did Sir say? If you, I can't exactly recall.
so it's before this. It's before this. Go.
Right here.
No, before, even before this.
Uh,
Ah, yes. So
okay, fine. Okay, this is what you're talking about when you mean coefficient. Fine.
yeah. So we're just trying to find out the cost with some coefficients and then updating the coefficients after finding the derivative. With respect to the coefficient, we are taking with
Okay.
derivative of the cost. So I wanted to know whether minimizing, what are we trying to minimize? Minimize the cost cost function with the current coefficient, or what is error function in this option? Is it same as cost function?
Okay, I get. See, okay, so you must, so this form of gradient descent actually it comes from linear regression. So if you try to derive the like gradient update rule when it comes to linear regression, right, you'll get like this formula: v is equal to v minus alpha delta j, and delta j is like the standard. Um, okay, fine. So, so so you want to know if this cost is the same as this, right?
No, this is same as that. I'm talking about the option error function. What is the error function?
Hmm. So we haven't
In the
discussed
option,
this. Sorry.
error function is mentioned in the option, which you are saying is correct. So is this error function same as our cost
Oh,
function?
is error the same as cost? Yeah. Yes. Hmm. Yes. So you could say yes. That's what I mean by error actually. So so the cost is actually calculated as like of course there are many ways of calculating cost, but like one way is you can calculate as a sum of the squares of the ground truth and whatever is your prediction, right? So
Okay.
so like you could say like the cost is like a function of the error. And you want to know about cost and loss, right? That is also one more thing, if I'm not wrong.
I think the loss function and cost
They're
function,
this,
they're interchangeably.
yeah, they are like interchangeably used. That is true. But like but in machine learning we, okay, yeah, they are like definitely interchangeably used, but like see, it's kind of, the cost is like it's a lot more general. Like what I've seen is cost is a lot more in like reinforcement learning, right? The cost of an action, but you see loss kind of more in like supervised or sorry, you'll see loss more in supervised learning, as in you can say that, let's say you make a faulty prediction,
Hmm.
you make a faulty kind of prediction, so now you have like a higher cost or something like that. So higher loss, like you make a faulty prediction, you have a much higher loss. But if you take a wrong action in an environment, you could incur like a much higher cost in
So
reinforcement learning. Yeah.
So your error is basically directly proportional to wrong,
Mm-hmm.
uh, and that is directly proportional to cost. Whatever we are trying to minimize in that algorithm
Yeah.
means
Error
error
is
directly
the
pro-
equivalent of, you could almost
yeah,
say it is equivalent almost,
yeah,
but it need not be like proportional exactly. There could be, it could be a function of
function,
a
random
function of
function.
the loss. Yeah. Mm. Okay, so how does federated learning differ from traditional centralized machine learning? Is it A, federated learning requires data to be pooled in a single place for processing? Is it B, federated learning involves training models separately at each client without exchanging raw data? Um, is it C, federated learning relies on cloud computing for model training? Is it D, federated learning is not suitable for edge computing environments? Any responses? Anybody has any responses? Okay, so the answer to this is, yeah, okay, B, yes. So in federated learning, what happens? You train a local model, you send the local model over a channel to the cloud, and the cloud or some kind of central server, and the central server kind of aggregates all these models, right? So that's why training models are trained separately at each client without exchanging raw data. So, what is the purpose of federated averaging in the federated learning process? Is it A, to initialize the model parameters on the central server? Is it B, to aggregate model updates from multiple clients? Is it C, to calculate the gradient of the cost function? D, to select random clients for model training? Can you, anyone has any responses? Acha, B. Panindra has said B. Okay, yes. So the answer is B, to aggregate the model updates from multiple clients. So when you have a lot of models, you want to put them together, use federated averaging, and to initialize the model parameters on the central server. No, that's not true. Averaging happens at the end once the entire learning process is completed. Calculate the gradient of the cost function. So you can say that well, okay, cost not exactly. You can say the loss function would be more appropriate, but uh, the gradient is calculated using like something like the chain rule, or we take the derivative of the loss function to calculate the gradient, and but the update of the gradient happens through gradient descent. To select random clients model tree, no. So once again, averaging happens at the end before the selection of clients. So next one, what is one of the key advantages of federated learning mentioned in the text? So A, it involves centralized data storage. It requires high bandwidth for data transfer, or it allows for privacy preserving machine learning, or it involves sharing raw data across all the nodes. Yeah, so it does involve privacy preservation. Um, yeah, Wi-Fi down. So yeah, so it does allow for privacy preservation, um, but why not the other ones? So why would it not require high bandwidth for data transfer? Okay, yeah. So yes, so the answer is definitely C. Okay, it allows for privacy preserving machine learning, but the answer is not B because like see the model updates here are in the form of gradients, right? So these gradients are just simple floating point numbers. So the size of the model may not really be as huge as the size of like the accumulated data. So like the model, the data size may be like about 2 to 3 gigabytes on each model, but the on each device, but the model may only be like a few megabytes. That is why the you don't have like that high bandwidth. That's why it does not really require that high bandwidth for data transfer. So B is not the right answer. C is the right answer. And of course, sharing raw data across all nodes, that is not true. Like we want to make sure that the data is not like transferred. It involves centralized data storage. No, like data is distributed. What is the technique? It's not the primary technique. So what is the technique used by Apple Siri for privacy preserving machine learning? Is it A, gradient descent, B, federated learning, C, differential privacy, or D, data aggregation? Federated learning is used. Can we make this multi-correct? What if this was multi-correct? How would you answer then? So gradient descent, federated learning, differential privacy, or data aggregation. So federated learning is used, but it was also discussed in the notes that differential privacy is also used, right? So if you go into Apple's example, it says over here that it in addition to federated learning, Apple uses something called differential privacy to add a further layer of protection. So this technique injects a small amount of noise into any raw data before it is fed into the local machine learning model. Okay, so the answer is uh, B and C. Okay, federated learning and differential privacy. Here are the two techniques. So how does federated learning ensure privacy while training machine learning? Is it A, by sharing raw data across all nodes? Is it B, by aggregating model parameters instead of raw data? Is it C, by centralizing data storage for analysis? Or is it D, by transmitting data to a central server for processing? Hmm. So the answer is definitely B, by aggregating model parameters instead of raw data. So what is happening is since you're not sending the raw data over to the cloud, since you're not sending the raw data to the cloud, you're and you're sending the model parameters instead, you cannot very easily see peek into the raw data from the model parameters. Even though there may be some techniques, but it's definitely not very easy to do it. Okay, to look into the raw data. So that is why you can say that it is by aggregating model parameters instead of raw data. So how does differential privacy contribute to safeguarding user privacy in series operation? So is it A, it encrypts all the audio data before processing? Or is it B, it adds noise to raw data before feeding it into local machine learning models? Is it C, it stores all user data on Apple's cloud servers? Is it D, it restricts access to Siri's machine learning algorithms? So please, I apologize for the background noise. We have some internet issue over here. So it does not really store all data on Apple's cloud servers, right? So, so the answer is B, right? We just discussed. It adds noise to the raw data before feeding it into local machine learning models. So even when you try to probably peek into the like federated learning models, it will you won't be able to access the data. So that's what differential privacy kind of does. So why is learning from non-IoT data challenging? Is it A, each IoT device requires a different model direction? Is it B, non-IoT data lacks variety? Is it C, models converge faster? Or is it D, IoT devices share identical data distributions? So what's the answer to this question? Why is learning from non-identically and independent data challenging? Is it A, each IoT device requires a different model direction? Is it B, non-IoT data lacks variety? C, models converge faster? Or is it D, IoT devices share identical data distributions? Yes. So what's going to happen is if you have if you have non-identically non if you have data that is not independent and identically distributed, so what is going to happen is each of these different devices is going to require a different kind of model, its own kind of model. So when you aggregate it, like you may not, and let's say send it back to each device for, let's say, local inferencing or something like that, you won't be able to, like that model won't work well on each device because each device has a different requirement for the model, right? So I hope that's clear. Okay, fine. Next question. Oh yeah, and D is obviously wrong because IoT devices need not necessarily share identical data distribution. So the devices can have non-identical and non-independent data distributions. And models need not necessarily converge faster if in non-IoT settings. In fact, they may even converge slowly because it may be harder to come to like a consensus about what would be a good model. So what is one consequence of very different data distributions in non-IoT scenarios? Is it A, smaller model parameters? Is it B, faster convergence? Is it C, requirement of a large number of model parameters? Or is it D, reduced need for collaboration? So what is the answer to 2? What is one consequence of very different data distributions in non-IID scenarios? Requirement of a large number of model parameters. Okay, let's take a look at your notes, by the way. So if data distributions are very different, learning a single model which performs well for all IoT devices may require a very large number of parameters. Okay, so so now this is, you could say this is kind of to accommodate for the various different kinds of data, different kinds of inferencing. Okay. So what does federated averaging experience in non-IID scenarios? Is it A, increasing local updates, B, decreasing learning rates, C, enforcing collaboration among, let me just remove this, among IoT devices, or is it D, it suffers from client drift? So the answer is correct. It suffers from client drift. So why is that? So you may not really know what client drift is, but the main idea is, like, let's say the model kind of learns something, but like the data distribution is completely different, so the accuracy will change. Let's look at client drift, the definition of that online. So okay, so I cannot find a very good definition, but the main idea is like some kind of forgetting can happen. Okay, if the data distribution like suffers like very significantly. And also in general, there's this thing called data drift. This might be kind of related to client drift. You say that changes in the distribution of the features of an ML model is in production while potentially causing a decline in model performance. So you can kind of say that data drift may be kind of similar to client drift as well. Okay, as in like the model, like the distribution of the client, like it kind of differs from whatever the model has learned during training. So that could be a definition of client drift over here. So now fewer local updates and or like smaller learning rates may have to be used. So what is the key difference between distributed learning and federated learning in terms of data distribution? So is it A, distributed learning requires data to be generated locally. B, distributed learning involves centrally stored data in a data center. C, data distribution distributed learning is non-IID. FL uniformly distributes data across workers. Any responses? So see, in distributed learning, the data is present centrally, and that is like distributed later, right, down to each user, down to each client, right. So that is why you can say, let's take a look at your notes, by the way, if it says anything over here. So in distributed learning, data is centrally stored, and then this data is actually distributed across workers. But in federated learning, you don't have that kind of control. So how is data distributed across workers in distributed learning? Is it A, uniformly across workers? Is it B, centrally stored in a data center? D, C, non-ideal distribution? Or D, imbalanced distribution? Any responses? Okay, so the answer to this question is uniformly across workers. So data is generally they try to distribute across workers uniformly, otherwise you won't really get the kind of results. So we control how data is distributed across workers. It is distributed uniformly at random across workers. So what characteristic of data distribution distinguishes federated learning from distributed learning? Is it A, central storage in a data center, B, uniform across workers, C, imbalanced distribution, or D, non-ideal distribution? Okay, does anyone have any responses? What characteristic of data distribution distinguishes federated learning from distributed learning? So I'm sorry. I think I'll just end the meeting now. I'll just finish this one last question, and I'll end the meeting. Okay. Uh, when I'll just do one last question, then I'll end the meeting. Okay. Fine. So, what characteristic of data distribution distinguishes federated learning from distributed learning? The answer is A, is D, non-ideal distribution. So in distributed learning, we want to make sure that the data is identical and independently distributed. So that kind of helps this entire situation. That kind of helps the make sure that the model is performing well. Okay. So everybody, thank you for attending like 8 weeks of problem solving. And if you have any questions, you can What is an alternative to the Carmel filter? I don't know actually. Uh, there may be other filters as well. Uh, there may be other filters that may give the same results. Maybe some machine learning techniques, but I'm not aware if there are any alternatives. Do you think 1 week is enough for me to study week 1 to 7 content? Uh, I don't know. That depends on you, right? So perhaps I would recommend that you go, you know, you can probably try to do as many questions as possible. Okay, and it could be possible. So you have to watch 20 lectures, right? And you may have to watch it like once or twice. So in that sense, okay. But everybody, like, thank you for attending 8 weeks of problem solving. It was really nice to have you here. I will be sharing the PDF of this content as well. Um, it will be available in the public sheet. Okay. Okay. Thank you, everybody. It was nice seeing you. You can contact me on this rachitvarma.ea@gmail.com. Thank you, everyone. I'm sorry I couldn't do like week 3, like lecture 22 as well, but I have some questions. I will like share it with you. Okay. Okay. Thank you, everybody. Thanks a lot. It's very nice. Thank you for attending. Regarding research doubts, further we may ask. Yeah, sure. You can email me. I'll be leaving now.